Hi, I'm Brian Davis, and this is my video presentation on my BTech final year project done in FISAT in the year 2020. We live in an era where corporations find themselves replacing modern-day wage slavery with automation. While the ethical dilemmas of such a problem are debatable, technology is never inherently evil, and it is undeniable that robotics has found itself the cornerstone of most technological progress in the 21st century. It has enhanced human capability in almost every field, including manufacturing, industry, prosthetics, and medicine, just to name a few. Nearly all of robotics is governed by a set of kinematics problems, namely the forward and inverse kinematics problems. Assuming that you have a robotic arm, forward kinematics is the problem of finding the position of the end effector if you are given the angles of each joint. This is a fairly simple problem and can be solved using just a bit of trigonometry and matrix multiplications to make it faster. Inverse kinematics, on the other hand, is the problem of finding the joint angles given the end effector positions. The reason this is so much harder than forward kinematics is because the problem has infinitely more solutions if the number of joints exceeds the number of dimensions the arm resides in. While there exist classical solutions to inverse kinematics, they are often bulky and not very scalable to large DOF values or degrees of freedom. This is where we try and use machine learning to make accurate approximates of joint values given the end effector positions, thus allowing these arms to work in real time without any prior hard coding of angles. Now that the terminology has been sufficiently explained, our project's aim to create a solution to the inverse kinematics problem using machine learning should be more self-evident now. In our project, we mainly focused on tentacle or trunk type robotic arms which have a single end effector and a huge number of DOFs. They are named as such because of their biological inspirations in octopus arms or elephant trunks. These type of robotic arms are now fairly simple to create but unwieldy due to how complex their inverse kinematic solutions are. Nevertheless, they find a use in some industrial scale applications and surgery wards. We created two separate models: the feed-forward network, which was created largely as a sanity check and as a proof of concept, and the recurrent network, which was inspired by a 2017 paper by Sebastian Otte that used dynamic cortex memory cells to control an arm using back-propagated gradients. To train either model, our first task was to create a forward pose generator to build a training database. This was done by randomly initializing angles uniformly along the given angle ranges of each arm segment. Said angles are transformed into DH matrices which describe both rotation and translation through 3D space for any given arm segment. Any arm can be simulated by multiplying each segment's matrix recursively until we reach the end effector. The feed-forward model was created using 7 layers of 256 neurons each, connected via a leaky rectified linear unit activation function, and was implemented as such. The recurrent model was created using a simple RNN with varying hidden neuron sizes. The hidden layers were connected to each other via a sigmoidal activation function, and the hidden layer was connected to the output layer via a linear activation function. The network was implemented as such. The feed-forward network, as predicted, works well for when the DOFs are under or less than the number of dimensions the arm resides in, as there is only 1 or 2 solutions in such a case. The results are as shown. The recurrent neural network, although promising an idea, showed very poor accuracy in the forward kinematics problem, which guaranteed massive jitter when trying to use its back-propagated gradients to solve the inverse kinematics problem, and was thus abandoned. But its results are as shown. In conclusion, this project has researched the usage of machine learning in the field of inverse kinematics and has constructed an inverse kinematics controller using a feed-forward network for demonstration. We have also experimented in the usage of recurrent neural networks to try and make an inverse kinematics controller with minimal complexity, regardless of the degrees of freedom. It shows promise, but has not come to fruition yet. With faster computers, better algorithms, and more programmers than ever, the future of robotics looks bright. Perhaps a bit of machine learning is what the field needs to tip itself into a golden era. Regardless, thank you for watching my presentation.